This is a short presentation on network density of states, a paper to appear in KDD 2019. My name is Bindel, a PhD candidate in Center for Applied Mathematics at Cornell University. This is my joint work with Austin Benson and David Bindel. The topic of our paper is spectral graph theory, which is closely connected to spectral geometry. Both areas study the spectral decomposition of operators, but one on graphs and the other on manifolds. Two fields share many common themes, such as dynamics, connectivity, and geometry. Particularly, geometric properties of the underlying object are often associated with the distribution of eigenvalues. However, many questions remain on this front for spectral graph theory. How do we compute the spectrum for large real-world graphs given the cubic scaling of spectral decomposition? What geometric properties can we infer from it? These are the questions we try to address in our paper. The object we compute is called density of states, also known as spectral density. Given a symmetric graph matrix and its eigendecomposition, density of states is the average of direct delta functions at the eigenvalues. Local density of states weights these delta functions by the contribution of eigenvectors in a given direction u. For example, when u is the indicator vector for a node, we get the pointwise density of states, capturing the contribution of that node at each eigenvalue. Here is an example for DOS and PDOS on an autonomous system network from 2000. On the left is a spectral histogram generated by integrating the DOS over the range of each bar. It well approximates the count of eigenvalues in these intervals, which is represented by the red dots. On the right is the corresponding PDOS, where each row is a weighted spectral histogram like the left for a node, and we stack across all nodes vertically. Red means a node has a high weight in the eigenvectors around a particular eigenvalue. To generate these plots, naive approach would require computing the complete eigendecomposition, which is order n cubed. Here are the main methods we propose. First is the kernel polynomial method based on Chebyshev polynomial expansion of DOS and PDOS. As an alternative, we adopt Gauss quadrature with Lanczos, which uses quadrature weights to estimate the same quantities. Combined with stochastic estimation, these methods have a complexity that is linear in the number of nodes plus the number of edges. In addition, we observe that an abundance of local symmetries can cause irregularities, such as high multiplicities around certain eigenvalues. And pre-processing by filtering these motifs can significantly improve the accuracy of our approximation around these spikes. Because all our methods are matrix multiplication based, we are able to further improve the efficiency by using a nested dissection scheme. In our experiments, we compute and inspect the DOS and PDOS for a wide variety of real-world networks. We observe distinct shapes of spectrum across categories, greatly affected by the sparsity and irregularities of the networks. On the other hand, networks within the same category often have very similar spectral signature. Here is a table showing our computation time per moment on a single core. Our highlight is the Friendster online social network, which shows our methods can handle datasets with millions of nodes and billions of edges. In addition, they give ample opportunities for parallel computation. In summary, we develop practical methods to compute spectral density for large real-world networks. DOS and PDOS facilitate insightful comparisons among graph datasets and models. They also provide new families of features for graph-related applications. Our implementation is available at the link below. If you're interested, please visit us at the talk. Thank you for listening.